And okay, so now we will continue now by looking at ADC. So because now we have at least enough background knowledge about DAC, so we will make ADC using DAC. First, looking at SAR ADC using parallel charge-based DAC, and then pipeline ADC. So I recommend to use these two references now for this lecture onwards when we are talking about ADC. I found chapter 34 from Mixed Signal Circuit Design of Baker is as a good reference for this part. And regarding fraction of bits per stage for pipeline that we will learn today, you use Maxim application node, of which the link is given here. Okay, so therefore we will now switch to continuing these two. And just I will tell you one small configuration. It is easy to understand it just as an alternate for DAC. I don't explore it. It's very easy to understand. Just is again one another. So because one architecture we explored in the last quiz, right, R2R ladder for DAC. So similarly you consider same R2R ladder. So I just, because here we have current sources, I put them over here. Again R and 2R, same as before. But instead of using voltages, we will use current sources. So here there will be a switch. Which will be either connected to ground or connected to a constant current source. Similarly over here. One of these two states. And so on. Similarly for the last one, I don't draw it, it's same thing. It's just same as quiz question. It's same as that. Instead of controlling these points which are connected right now to ground, bottom terminal of 2R resistors to V full scale or ground. Now we are, instead of that, because what it was doing, it was actually injecting current to this node and then to RF. So now we are injecting current directly by using a current source, and that current source is constant. Value of resistors again are not binary scale, is R2R ladder. So the benefit is that here you will get a constant current for switches. So you can use same sizes for all switches. However, still internal nodes are changing. Therefore, here you have the same trade-off. Either you will get different drop across switches, or you will get different voltages on internal nodes. One of these two. If you want to keep them constant, then you need to resize switches for different bits. If you don't want this scheme or another scheme that we had, then you will have variation of internal nodes. This is just for your information, and it's easy to understand it. So now we will start by looking at how we can use this parallel charge distribution, or sometimes it is called charge scaling, parallel charge scaling, in a binary weighted capacitor array to make a SAR ADC. Okay, so I start from here. I try to accommodate and explain it. So essentially what we want to do, okay, let us put at least block diagram over here. Now what we want to do in SAR ADC, so the main point was to use a DAC. Okay, so this is DAC. Output of DAC will be given to a comparator. And this is your V. Okay, and then output of comparator will give you one bit, which will determine whether assumption of the current bit to be 1 is correct or not. If output is, for example, if you consider the current bit is 1 and it appears that Vin is less than that, therefore your output becomes 0, therefore you will change the current bit to 0 and you will proceed. So this was the operation of SAR ADC. Now what we will do is, we need to see how we can have this Vin. First of all, this Vin cannot be analog Vin. Therefore, you need to have a sample and hold or track and hold, in fact, version of Vin at the input of comparator. So therefore, this Vin should be track and hold. This is one thing. And the remaining part is same as before. So here you will have that control you need. And this is now your parallel charge scaling DAC. Okay, so this will have enough number of control lines. So the one thing which comes to the mind is, see, DAC, this DAC, if we are using a charge scaling DAC, so it has already capacitors. Can I use those capacitors to sample input signal on that as well? And therefore, I don't need to actually put a separate again capacitor for track and hold. So what we want to do is that make a simplified version, because this is quite straightforward. There is nothing here to show. But there is an alternate version which is usually used, and the main reason is that there you don't need an additional track and hold. The same capacitors which are used for charge distribution and charge scaling are used also to sample input signal. So it saves the number of capacitors, and therefore you will have a more cost-effective version of this SAR ADC. Therefore, just we will have same thing, only now we will sample signal also on the same capacitor array. That is the only difference. So now what we want to do is that, so this is the sample, in fact the comparator. So what it does is that you remove Vin, okay, you make your reference, for example, ground. Right now, first I start with ground level, 0 level as a reference, then if there is a common mode level, I tell you how to shift it and what are the changes in the circuit. Just for simplicity, consider you have a ground. And here what you need to have, instead of comparing Vin with output of DAC, right, what you are doing here, you are comparing Vin whether it is greater than DAC out or not, right? So equivalent with that, you can say, I am looking at Vin minus DAC out, whether it is greater than 0 or not, right? So therefore, what we do is that, instead of comparing Vin with DAC out, we will compare Vin minus DAC out, or DAC out minus Vin with 0. So that is, and therefore, now when we say this subtraction actually is done on the capacitor itself. So therefore, we sample, subtract, and compare it with 0. So this is the whole idea behind this cost-effective or component-effective SAR ADC. So now, we come back to that binary weighted capacitor. C, 2C, so this was the original one, right? Before using an op-amp, it was the passive part without any op-amp. So we had this configuration, okay? So now, bottom plate of these capacitors if you remember, we had 2 choices. Now we will have 3 choices. So therefore, it will be either connected to ground, or, so therefore this was one possible choices. When I use arrow, so this is our notation, means that this is one possible case, or another case would be to connect it either to V full scale or V in. Therefore, eventually you have 3 choices, either this or this, and eventually. So either connection to ground, or connection to V in, or connection to V full scale. Okay, that is the reason now we will have 3 levels. The same thing will repeat here. So I don't show it, but just I am showing that, okay, this branch is here, again this branching is here, this branching is here. So it will repeat the same way, and finally again you will hear either V full scale or V. So the switch which is doing this transition, we call it S2, and because here all these transition are simultaneously, eventually these 2 transitions happen at the same time, in the sense that if you connect the bottom plate of C to V in, all will get connected, or all will connected to V full scale, or any one of them then will be connected to ground. And then upper plates are connected the same way it was in the passive charge scaling, and then you have a switch S1, and this was the output. So this is eventually like that, you had a connection to ground or V full scale. Now we have a sampling switch which allows us also to sample input voltage on the capacitors. So just to make it simple, we go with n equal to 4. Therefore we will have C, 2C, 4C and 8C capacitors. Okay. So first of all, you will reset all capacitors. Therefore, reset is very easy, means that you need to connect all top plate and bottom plate to ground, make sure all capacitors have 0 charge. So this is quite straightforward. The next step is to sample V in on the capacitors, right? Because before doing any comparison, we need to sample V in on the capacitors. So therefore, first phase will be reset. This is obvious. So we will go now with how we will proceed. To do any comparison, you need to have sampling. So therefore, first phase will be sampling. So in sampling mode, what we want to do is to sample input signal. So I don't draw again, I call this capacitor array. So you have a capacitor array. So bottom plate of all capacitors is connected to V in. And this is that switch S2 which is closed. Okay, so bottom plate of all capacitors using switch S2 is connected to V in. Therefore, and bottom plate, upper plate using switch S1 which is closed now is connected to ground. And of course, the output of this capacitor array will go to the comparator. This is comparator. So what it does means that when you come back here, so what we want to sample input. Therefore, it is obvious that we have to connect the upper plate, for example, to ground, lower plate to Vin. Now, all capacitors will have Vin on their own, right? Therefore, all capacitors will have Vin in this way. This side is Vin, bottom plate, upper side is connected to ground. Therefore, you will have this polarity Vin. Okay, so now you have sample Vin now on all capacitors. So this is eventually Ci, all capacitors. Ci and C and Ci, because we have one additional C. In our case, I is changing from 0 to, we have total 1, 2, 3, 4 capacitors. C0 to C3. So now all capacitors have, now you have sampled. So now we will go to the redistribution and comparison mode. So therefore when you sample, or it would be better to call it track because there is no ideal sampling, it's track mode. So therefore if you hold it, in fact I can make it separate, or I can say that, see what is in hold mode. Okay, so you track, you sample and then you disconnect. Therefore in hold mode all switches are open. So means that you have this capacitor array. So now it's open. It's hold mode, right? So nothing is connected. Switches are open. It's just holding the input voltage on the capacitor. That's it. So anyway, this is also in general is 2 to the power n minus 1. Yeah? Cn? Ci are these capacitors. For example, this is C0, this is C1, this is C2, this is C3. These are Ci values. Eventually it's 2 to the power n minus 1, right? Here we have 4 minus 1, 3, so this will be 8C. So we have 4 capacitors. Okay, so now we will go in the hold mode. So in the hold mode everything is open, therefore nothing special is done. So now what we should do, what we want to do is start to generate reference levels, right? So to generate reference levels, now we will go again capacitor by capacitor, same as before. So now we will go with the redistribution. So therefore in redistribution mode, so first again MSB capacitor will be connected to V full scale. In this case it is 8C. And others will be connected to ground, which is 4C, 2C and C. And S1 is open, and this goes to comparator. Now what will happen? So let's draw the equivalent circuit. By the way, we know that at t equal to T0 minus, we had V in on all capacitors. So what is T0? T0 is exactly time when we connect this bottom plate of HC to V full scale and others to ground. So at that time we had VCI is equal to V in, and VCI is bottom plate minus top plate. So this is V in. This was the situation in the hold mode. Both sides were open in T0 minus. Now it is closed. So what is the equivalent circuit? So the equivalent circuit, eventually if I redraw it, it will be like this. And this is total summation of these capacitors, which is HC again. 4 plus 2 is HC. And this is V out, which is going to comparator. So this node is V out. Look at the polarity. So bottom plate of HC, which is connected to V full scale, had V in. So now bottom plate of other capacitors is connected to ground. Already it had voltage V in. So what we have done, we have just connected bottom plate to V in. Forget about full scale. If suppose you ignore full scale, the summation of voltages in this loop is 0, right? Therefore, adding to V full scale doesn't change the value stored on the capacitors due to V in. It only changes the value stored on the capacitor due to charge distribution as a new event due to change of this voltage to V full scale. So therefore, you can considering it as this. If you look at this situation, summation of voltages across these capacitors is 0. Okay? Therefore, either you keep it in this way, you connect it to ground, nothing changes. Now you are increasing this node by amount of V full scale. Suppose it was ground, assume it is ground. It's open, but it is anyway 0 level. Now you are increasing it to V full scale. So now what will happen? So eventually if this is V, your delta V is V full scale. So it is just like, look at this as an operating point. Look at what is your delta V, because this is a linear circuit. So you look at your delta V. Delta V is V full scale. Therefore, you will have a capacitor HC and a capacitor HC here. So you have changed by the amount of V full scale. Therefore, here your delta V out will be V full scale by 2. And original value was minus V in, right? Therefore, V out in T0 plus after charge distribution will be delta V out, which is V full scale by 2 plus original value, which was minus V in. So original value of V out was minus V in. This was V out. So therefore, now you will get V full scale upon 2 minus V. Okay, so is it clear? So now what will happen in this case? Now in this case, okay, so this voltage is given to the comparator. So what it does, it is comparing V full scale by 2 minus V. So now input of comparator having V full scale by 2 minus V. So there are two cases, either this is positive or it is negative. If V full scale by 2 minus V in is positive, therefore comparator output, because it is given to the negative terminal and this is greater than 0. So it is 0. If V full scale by 2 minus V in is less than 0, then comparator output will be 1. This means that V in is less than V full scale by 2, therefore comparator output will be 0. So according to this, we will decide what will be the next stage, right? So this means that now MSP should be 0. So the first assumption that we considered MSP to be 1 is not correct. And here means that MSP should remain as 1. So in both cases, we will go to the next phase to see what are the differences. Then after that, everything will be repeated. Therefore, we will have 4 case MSP equal to 0. So next phase, we will go to the next bit considering now MSP has been 0. So V in is less than V full scale by 0. So because MSP has been 0, therefore capacitor HC, which was connected to V full scale, now will be connected to ground. Bottom plate of this capacitor now will be connected back to ground. And now next bit, which is related to capacitor 4C, will be connected to V full scale. So this is assumption for that, and again we connect them to ground. Others will be as before connected to ground. 2C, C, C, and this will be connected to comparator. And upper side also is open. Always this is open during evaluation mode. Now what is the equivalent circuit? This is just a matter of difference. Now we will take 4C out to show this. The reason I am drawing in this way, just to show you the capacitive division. And this will be 8C plus 2C plus 2C, which is eventually 12C. And this is V out. Now look at the distribution of V in. Again, you have this V in on all capacitors, and for 4C, because bottom plate is connected to V full scale, so this is V in. Again, if you notice, there is no change in the total voltage across these two capacitors, 4C and 12C, due to V in. Therefore, there is no change there. So V in will remain as it is. Means that sample V in always will remain on the capacitors. So what will change only is the capacitive division. So again you have your delta V equal to V full scale. If this is open, this will be 0, or you can connect it to 0. Results will be same. Therefore, when you connect it to 0, initial voltage has been 0. Now you are changing it by the amount of V full scale. Therefore, delta V out will be 4C upon 12 plus 4, 16C, V full scale, which will be V full scale by 4. So this is delta V out. Therefore, V out is equal to minus V in, original value, plus V full scale by 4. Means that if MSP is 0, now we need to compare it with full scale by 4. And therefore, now again it will continue the same way. And the other case, which was MSP equal to 1, we cover it. Okay. So if MSP would have been 1, therefore we need to keep HC connected to V full scale. So HC will remain connected to V full scale. Now 4C also will be connected to V full scale, and the remaining capacitors will be grounded as before. In fact, this is very similar to the previous analysis, only you have a V in sampled on the capacitors, that's it. 2C, C, V out. Again, this is connected to comparator. So, it is same as before, only now, again same thing will happen. Now, what we have here, so we had this V full scale, yes. So we had this V full scale now connected to 4C. So we had already this situation here. So now we have 4C connected. So before connection, first let's make it, say for example, T1 minus. At T1 minus, what has been the situation? This capacitor, this was V full scale, this is 8C, and the voltage here, if you look at voltage in this way, this is minus V in, minus V full scale by 2, right? This was the condition. And other capacitors were connected to ground. And total value was 8C, right? So no, let me separate them because 4C will get connected to V full scale now. So 2C. So this V full scale, therefore you had V full scale by 2. It's this here. We had V full scale by 2 minus V in this side, and this is V full scale. So it will be V full scale by 2 minus V in, from left to right, means from bottom plate to this side, we will have V full scale by 2 minus V in. Okay, so therefore this will be, no, sorry, here, I will just write, at T equal to, so this voltage V8C, V8C is equal to V full scale by 2 plus V, right? It's a difference of V full scale and V full scale by 2. So it will be V full scale by 2 plus V in. This is the voltage across capacitor 8C. If polarity is bottom plate minus top plate. Here I have written top plate minus bottom plate, that's why they get multiplied by a negative. And for C, it was parallel to this, therefore V out was V full scale by 2 minus V. So here also we will have same thing. So this voltage is V full scale by 2 minus V. So this is condition at T equal to T1 minus. So now we will go to T equal to T1 plus, right? What changes here? Now I will show only changes. So this 4C now will get connected to V full scale, others will remain as they were. This was 8C full scale. C, 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 and finally V out. Okay. So summation of this 4 is 4C. So this is 4C. I just combine them. This is 4C. I use this 4C. So now the only change is this bottom plate of 4C, which has changed from 0 to V full scale. right? So therefore, what does it mean? Means that again we will go with that small signal analysis, because nothing changes here. V in doesn't change as such, because see here again you will have same condition. This is V full scale, this has been, okay, because it is plus, I don't write, you look at here, because this is T1 plus, values will change. So in T1 minus, if you look at this loop again you will have plus V in minus V in equal to 0. So as far as V in is concerned, nothing changes, V in will remain as it is, only we have a change or jump from 0 to plus V full scale at bottom plate of 4C. Therefore that delta V here, if we call this V star, delta V star is equal to V full scale. So therefore again we will go with that delta V. So V out delta V out is equal to, so we have 4C this 4C. This 4C divided by whole values, which is 16C, 4 plus 8, 12 plus 4, 16, again same thing, and this was V full scale, right? Delta V star is V full scale plus original value, right? This is delta V out, so it is V full scale by 4. So what was original value of V out? Original value of V out was V full scale minus upon 2 minus V in. Therefore V out now at T1 plus will be V full scale by 2 minus V in plus V full scale by 4. Which will be eventually 3 V full scale by 4 minus V. So therefore, if MSB is 1, now V in will get compared with 3 V full scale by 4, and then if MSB is 0, V out will be V full scale by 4 minus V in, means V in will get compared with V full scale by 4. So is it clear? So these are main phases and the story repeats. Yeah, V full scale. It's already connected. It's not a change. What I have done, T1 minus was this. Means that 8C is already connected to V full scale. This is not a part of new condition. This is old conditions. The only change we have here is this bottom plate of 4C. So when I consider initial condition, I consider bottom plate of AC is connected to V full scale. And therefore, the initial condition that we have is after charge distribution by connecting bottom plate of AC to V full scale. So now this is initial condition for the next phase. Therefore, there is no change. If you look at delta V at bottom plate of HC, it is 0, because still it remains to V full scale. So delta V here is 0, delta V here also is 0. You have only one delta V here, which is V full scale. They are not parallel in the sense that they have same voltage across them. What we are saying that is that we are looking at delta V, making it, because circuit is linear, so therefore it's like a small signal analysis. I consider this is my operating point, then I consider only small signal variations, and then I add this to operating point, I get new values. It's exactly that. So in fact, if I want to show that a small signal model, here will be delta V and all will be ground, right? Delta V is 0 for all of them. Therefore, you will get this delta V out equal to V full scale by 4. However, as I mentioned last time, every time you are connecting to V full scale for charge distribution, and therefore you are spending energy. So you can look at Vinayak paper as well as its references for different recently reported configurations of SAR ADC, which have looked at how they can make it more efficient with respect to energy. Therefore, this standard, in fact, way of switching now has changed. So this is very basic method which was reported long time ago, but now they are making different switching arrangement to save energy. Instead of connecting to V full scale, every cycle you are connecting to V full scale. Oh yeah, because this is not a very high speed. Therefore, SAR ADC is not a high speed ADC. Therefore, eventually what matters at the end is for every bit you generate, how much the energy you dissipate. Doesn't matter how long it takes time, because here we are not talking about a high speed ADC. Therefore, energy per bit is a better criteria. Yeah, exactly, because here we can make it more energy efficient. And of course, to make it, you need to reduce frequency again. You cannot keep frequency same as this scheme, but it is good enough still, because by operating it at lower technology nodes, you will be able to achieve better speed. Of course, your inaccuracy problems also will be more, but overall, you will be able to get a good speed. Hundreds of kilosample per second is a good number for many applications. Even it is possible by a good design to bring it to megasample per second, which is quite good enough. Okay, so this was an example. Now we will go to pipeline ADCs. So Baker, chapter 34, Baker has a good analysis about some of the issues in pipeline ADC. That's why I recommend you to look at it. I will explore it more. Like for example, when we go to pipeline, we need to sample again, and then we need to multiply by 2 or multiply by some 2 to the power m. But what is important is we can do all in one. So details of the architecture we will cover next session, when we are starting now to looking at the details of implementations. But now just look at the architecture and what are the problems and essentially pros and cons. A little bit we covered in the previous lectures. Now I will go deeply into the pipeline architecture, what it does and what it doesn't do. Okay, so this is a new part. So the whole point was, if throughput is only important and if latency is not important, therefore pipeline ADC is a good high-speed ADC. But if suppose you are using it some control applications and latency is important, therefore pipeline ADC won't be useful because it has quite a long latency at the beginning. Okay, so what a pipeline ADC does? Pipeline ADC says that instead of parallel conversion, make it sequential. After all, either it is series or sequential, parallel. But instead of making bit by bit, you can make it 2 bits per stage, you can make it 4 bits per stage and 3 bits and so on. Eventually what it says is that you divide your conversion to n cycles. So it's like SAR ADC. You were doing every cycle 1 bit conversion and then it was a sequential conversion. Here also says, okay, you do it in sequence, don't do it in parallel like flash. However, you can choose to have more number of bits than 1 in per stage, or if you want you can make it 1 bit per stage. Let's suppose we have 1 bit per stage. What does it mean? Okay, so we have same stages. So then we will show one stage, and this is your V in. So this is very crude type of pipelining. So you have a V in, you have a 1 bit ADC here, can be a simple flash. 1 bit ADC is very appropriate kind of ADC for flash architecture, gets most of it for speed. So here you will, now you have clock cycle. For example, I called it cycle n. This is cycle n plus 1. This is cycle n plus 2. This is cycle n plus 3. So conversion cycle may not be 1 clock cycle, it may be more than 1 clock cycle, okay. So you may have more than, but so this is for example conversion cycle we are talking. So first you will do 1 bit, so you will get MSB bit. So here I am giving like sample of 4 bits, so you will get B3 here, B2 here, B1 here, and B0. So what does it mean? Means that in cycle n you will get your B3, in cycle n plus 1 B2 and so on. Therefore you when you reach to cycle n plus 3, all bits are ready for sample which was generated at cycle n. Therefore if you track and hold at n, then bits are ready at n plus 3. This is latency, right? So, but not all bits, only the last bit is ready at n plus 3. The bit before that is ready at n plus 2. Therefore, you need to store this bit somewhere. And then when you require, then bring them all together to the output. Therefore, you need to store this B3. So, therefore, you need to have some kind of, for example, shift register. So, therefore, B3 will go here, B2, B1, B0. Now, if you look at the output of this module, so this is a simple shift register. So, if you look at the outputs, then sample all outputs at clock or cycle n plus 3, then you will have all bits ready here. Okay, so this is a very crude way of doing that. And the benefit is that because now it's 1 bit ADC, it will be very fast. You need a very small hardware, and then you need to go to the next part. But how this is done, and then I mean mathematically how I can go, what is the output? For example, here the vertical outputs are of course bits, B3, B2, B1, B0. And this is for these cycles. Now, if you go for example, n plus 1, when you are at n plus 1 instead of B3, you will have B0 of the next cycle, next sample, and so on. So this is a pipeline kind of architecture. Now what is this output? What goes from one stage to another stage? And then here eventually we may not need that output. This one, these are 3 cells, means that in cycle n, B3 is here, in n plus 1, B3 will be here, will shift to second one, in n plus 2, it will shift to the third one, and then n plus 3, it will be at the output of third one. means that at the n it will be at the, here, it will be latch at the output of first one. Yeah, but numbers are, yeah, because the reason is that because these bits are not available at the same time. So therefore we need to take care of this delay. So your B0, when your B0 is ready, your B3 has been ready all before, 3 cycles before that. So where do you keep it? You need to keep it in a memory. Essentially you need a memory. This shift register is that memory. Yeah, okay, so let us put it, how this pipeline will be. Suppose now I give another index to this bits which will be equivalent to the sample number, okay. Suppose we have sample 1, okay, and I go as per clock cycle. So first you will have B31 and there is nothing here, B2, B1, B0. Okay, first one. Then you will have B32 and B3, sorry, this is B3, B2, yeah, sorry, B21, B32. Okay, nothing is here. Now you will have B, here will be now B2, B3. B2, sorry, this is B3, this is B2, then this will be B1, 1, then this is B3, this will be B3, 3, then this will be B2, 2, right, and so on. So now if you have this B3, next cycle this B3 will go away. If you don't store it, you will lose it. That's why we need this memory. So what happens inside the pipeline stage? So eventually pipeline stage, what does it say? First, suppose we have just one bit. Okay, so we have 1 bit ADC. And you have a drag and hold version of input. So therefore at the output either you will get 1 or 0. Therefore you need only one reference level, which is V full scale by 2. Right? This is your reference level. So now giving an example, suppose this is 1 bit ADC, this is V full scale 0, V full scale by 2. So you have a signal, for example, somewhere here. So output of 1 bit ADC will be 1. Fine. So therefore now you know that your signal is somewhere here. But you want to have more resolution than 1 bit. Now what you need to do is that the next step, what would be the next step? To compare your input V full 3V full scale by 4. But we don't have any 3V full scale by 4. This is just 1 bit ADC. Right? So what we need to do? So what we will do is that now I know my input is here. I know my input is on the second half. Okay. Now if I deduct V full scale from input, what I will get? So I deduct V full scale from input. Therefore now if I again keep the scale for ADC same as before. So I have 1 bit ADC, I cannot change my reference value. But what I can do is that I can now deduct V full scale by 2 from signal. So signal was V in was greater than V full scale by 2 and was less than 3 V full scale by 4. So I deduct V full scale from input. So therefore now V in minus V full scale by 2 is greater than 0 and less than V full scale by 4. Therefore if I look at this new scale, so I deduct. So now what does it mean? Means that I have gone inside this scale, which is half of the full scale, right? So I want to return it and scale it back. So therefore I will just multiply it by 2. So what does it mean? Means that now this 2 V in minus V full scale by 2 now will be between 0 and full scale by 2 somewhere here. It was close to 3 V full scale, so it will be close here. So now this new signal will be here. So therefore, instead of scaling reference values, I deduct closest reference value from input. I scale the residue. This is called residue. Therefore, still I can do operation the same scale of 1 bit ADC. So this is called residue. So this is for the case it was above V full scale. Suppose if it was below full scale. So suppose now, or your signal is here. This is V full scale, this is 0, this is V full scale by 2. Suppose your signal was somewhere here. Therefore your output will be 0. So here, because the closest level, which is smaller than your V full scale by 2 is 0, therefore you make V in minus 0 will be V in. Therefore your residue will be same as V in. Now you multiply your V in by 2. V in was less than V full scale by 2. Therefore 2 V in Okay, so suppose your V in is between V full scale by 4 and V full scale by 2. However, when you give it to 1 bit ADC, it will give you 0 because your input is less than V full scale by 2. Fine. So now it's less than V full scale by 2. Now we want to compare it with full scale by 4. But we don't have V full scale by 4. So what to do is that, and the closest level to V full scale by 2 is 0. Therefore, I will just make V in minus 0, which will be 0, and just multiply by 2. Therefore, now 2 V in will be less than V full scale, greater than V full scale by 2. Now what I have done is just I have scaled up again by a factor of 2. So now I can, instead of comparing input with V full scale by 4, I compare 2 V in with full scale by 2. It's same. So here residue is same as before, same as V in. So residue is V in, here residue is V in minus V full scale by 2. So in pipeline ADC says that if you want to use similar stages, say 1 bit ADC for all stages, you need to calculate first residue and then scale it up, and therefore again you use 1 bit ADC in the full scale. Vref by 2 will be your reference level. So therefore every stage of pipeline should do this job. Means that, so what it should do now, first of all V in should go to a track and hold, now making it more particular. Then it goes to the ADC, this is say 1 bit ADC. So you will get either 0 or 1. So you have your input ready over here. So the output, this output bit B is here. You give it to a DAC to generate actually in fact what this DAC does, it finds the closest reference level below V in. This is same thing. DAC always does this. So it generates reference levels for you. So here is another. In fact, you are subtracting. Here what it does, the output will be residue. The same residue will calculate it here for 2 cases. So now this residue will be multiplied by 2. Therefore, here you need an analog multiplier and then give it to the next stage. Sometimes in textbooks what they do is that they remove track and hold at the input of this stage, they add it to the output of this stage. Okay, but I think it's better to keep it at the input, because anyway the first stage should have a track and hold input. Therefore, I prefer to keep it at the input. So every stage of this 1-bit conversion is actually this. Therefore, what goes to the next stage is an analog value. And that analog value is the scale version of the residue. So therefore, now I will add this question mark, actually will be scaled residue. So the benefit of this work, though we need a subtractor, though we need a multiplier, but the benefit is that now you can use same stage and repeat it, just easily repeat it. However, this is for 1 bit, therefore you need 1 bit DAC. It will generate for you either 0 or VREF by 2. But you may want to do 2 bits per stage, because 2 bits also is not very expensive with respect to a flash architecture. So you can have 2 bits ADC per stage. So nothing changes, only your factor instead of 2 now will be 4. And then your DAC also now will be 4-bit DAC, 2 bits DAC instead of 1-bit DAC. So this DAC also will be 1 bit. If you make ADC 2 bits, DAC also will be 2 bits. Now there is this looks very nice, very good, and we will cover the details in the from next lecture. I will start looking at the details. So this residue is a subtractor, this is a multiplier, and it can be shown if you use a switch capacitor circuit, you will be able easily to make a subtractor and multiplier. It's not very difficult, because in switch capacitors you can make an amplifier with a gain of perfectly 2, ratio of 2 capacitors. And by changing the way you do switching, you can change the polarity. Therefore, you can make a subtractor. The same way we did actually here with SAR ADC. We subtracted signals, right? Just by proper switching, you would be able to do it. Therefore, implementation is not a big deal. The problem is with the errors. And why the problem is with errors? See, if this residue has some error, it will get multiplied by 2. Or it will get multiplied by 4, or whatever number of bits you have will determine. Means that if you have an error in one stage, it will get scaled up to and will go to the next stage. And therefore, it will get accumulated. Therefore, one of the main drawbacks of pipeline ADC is that if you don't care of this inaccuracies, actually middle stages may get saturated. Because if your error goes more than some value, you actually may reach to full scale level, because this is an analog level, right? This analog level, which is residue multiplied by a scale version of residue. Oh, this is a scaled up. Actually, I should call it a scale up, because sometimes a scale means a scale down. Scale up residue. So it is a scale up residue. So if you don't take care of this inaccuracy, actually you may reach to VDD level. And then the entire circuit will stop working. So that's why it's very important to take care. Now there are different methods how to do. There are calibration scheme, correction scheme. There is a very interesting method which says that, so now we will look at that method, and that Maxim application note as actually because of this. It has other things also, but particularly what we are looking in one of the methods to control this residue. So, is it clear till now? Now we can go with what the next step, what is the problem, and then how we can solve it. Yeah. Yeah. See, in SAR ADC, what you are doing is, okay, so let us come back to what makes the delay. So you sample input, you will have this charge redistribution, that is that delay of this charge redistribution, and then you have delay of comparator, and then it will go to control logic, and then it will set the next stage. So this is the delay of 1 bit. Okay. Now, when you go to the next bit, again you will have same delay. So suppose we call this delay TD for 1 bit generation. So the whole delay this SAR ADC will take will be NTD. If you have n number of bits and delay of 1 bit generation is TD, so you will get NTD. So this is the minimum time you need to generate 1 word, n bit word. Okay. Now you come back here. Practically delay you get here will be only 1 TD, not NTD. Why? The reason is that for first sample you will get some delay. That is same as SAR ADC. But for the next sample you get only 1 stage delay. Right? That's why first sample will have latency, and if delay for the first sample is important, then you should not go with this method. Otherwise, if only throughput is, you want to start working, but you don't mind how long, but then after that your samples will arrive every TD seconds. So therefore, we need track and hold to separate stages from each other. Therefore, when one stage is processing, the other stage should not get affected. So that is the reason we need track and hold. So, and the error is multiplied by 2, therefore, or 2 to the power m, therefore, we need to be very careful. So now what is the solution? So one solution. So, I mean, what kind of problem we are looking at? The problem we are looking is consequent multiplication. May drive ADC out of range due to errors. Okay, so this is the problem. So there are different solutions. So one solution. One of the solutions says that if you want to have 1 bit per stage, for example, don't limit your reference levels only to 0 and Vref by 2. Suppose if you have 2 bits per stage, therefore you will get better results, right? Because you have now 4 levels. You can determine the amount of error more accurately. Because you have 4 levels, you will deduct your residue now will be smaller. But if you want to make it 2 bits, for a given amount of resolution. Okay, so if you make it 2 bits, again you need to multiply by 4, so you don't get anything. From this side you are reducing the residue value, but again you are multiplying by 4. So problem is same as before. So why not to use 2 bits but multiply by 2? What does it mean? It means that you use redundant bits just for the sake of predicting your residue more accurately. More number of bits essentially means that you use more number of reference levels for every stage. Still it is 1 bit ADC. but you have redundancy. You are generating more number of reference levels, and this more number of reference levels helps you to determine value of residue with more accuracy, and then still multiply it by 2. So now what it does is that it tries to keep your residue always within some limits, and this helps to avoid overdriving. So the best thing will be to show it by example. So therefore one of the solution is use more VREF levels which is equivalent by saying more number of bits which will be eventually redundant bits, because we are not changing the scaling factor. What we are doing is that we are calculating residue with more accuracy. That's it. So now how this works. Okay, so now let's give an example. Suppose now I go with a 2-bit ADC, okay, 2-bit ADC per stage. However, I will finally generate 1 bit for a stage, okay, but effective bit per stage, effective NOB per stage equal to 1. So what we do is that now I will give you an example. Best thing. So now we will go with example. In fact, we don't go with any theory, just by example we show how it works. It is better for learning. Suppose we have number of bits per stage 1. Therefore, what does it mean? Means that because Maxim, oh by the way, I forgot to tell you about this V common mode level. In the case of SAR ADC, if you want to make it common mode, therefore this will be connected to common mode. This voltage also will get connected to common mode. Therefore, you will store value of common mode on the capacitors. When you are comparing V in minus Vref plus V common mode with V common mode. Therefore, that V common mode doesn't have any impact. So just these two will get connected to V common mode. Okay. So here also again I am using ground level or the 0 level, because in application note it is like that. So that is okay. So what I do is that instead of 0 and V full scale, I make it minus V full scale by 2, V full scale by 2 and 0. It's just the shift makes the reference level 0, middle reference, to be compatible with that. So we make it, how many reference level we have? Actually is 2, right? 0 and minus V full scale by 2. Or if we use positive values, it will be 0 and plus V full scale by 2. Total range still is V full scale. Okay. Now let us make n 1.5. So what does it mean 1.5? Eventually, I mean it is just a concept. It means that let's increase our reference levels to get better accuracy for residue. So therefore now same scale you have, minus V full scale by 2 plus V full scale by 2. This was 0. Now we add, instead of making 0, what we are doing, we generate 2 other levels. V full scale by 8 minus V full scale by 8. Okay, I think in the application note also, in many cases you see Vref. I mean, I believe V full scale is better because Vref actually is the reference level. V full scale shows you what is the total range you have. Now, what we do is that here how many in fact interval you have 2, right? And you check whether your input signal is in upper half or lower half. Here we divide it into 3, and these 3 are not of same magnitude. So see, number of levels are not 4, they are 3, and you have 2 bits eventually. That's why it is called 3 by 2 1.5 bits. I mean, that's why it is not, it is even conceptually called 1.5, because you have 2 bits but you have 3 reference levels. Means that out of these 4 possible combination, one combination of these 2 bits is of no use practically. So you are adding redundancy, but now you are predicting your, or in fact calculating your residue more accurately. Okay. So now what we will do, now what are the actually size of these values? So this is 3V full scale by 8. I mean, this is magnitude, okay. So this is magnitude. This magnitude, again this reference is V full scale by 4, and that is again 3V full scale by 8. So now still we will multiply by 2. Okay. So now if it is 1 bit scaled up residue will be 2 into V in minus V ref by 2 or 2 V in, right? One of these two, according to whether V in is in the upper half or lower half. And of course in this case, because we have shifted, so therefore I will have, I mean say actually it will be V in plus V ref, because it will be minus V full scale by 2. So according to the bits, okay, so either one of these two. Now here what it says is that in a scaled up, so it is the same as before. I mean multiplication factor is still 2, but instead of V ref by, sorry I wrote V ref by 2, it should be V full scale. V full scale by 4. So now that reference levels are here. So now we have these 2 reference levels. So we have 3. Whether it is less than minus V full scale, is between V full scale by 8 and minus V full scale by 8, and above V full scale by 8. So why we are adding by V in plus V full scale by 4? So because it is 2 bits. So eventually we could have done that, but we are multiplying by 2. Now what it does is that if your residue tries to become very negative or very positive, that is the reason next stage will suffer. So it will try to return it back to its original value. So for example, so now real examples, for example you will have, suppose V full scale equal to 2 volt, okay, and you want to have 1.5 bit per stage, therefore you will have plus 1, minus 1, 1 upon 4 and minus 1 upon 4. Okay. So I stop it here. I will continue it on Friday to eventually to discuss it more, how this residue will be controlled to remain in a given window. This one actually because this is minus V full scale. Oh no, what bit? Actually if it is 1, this is for 0, this is for 1.